There's something humbling about staring up at the night sky, isn't there? A vast, glittering canvas that seems to whisper secrets just beyond our reach. For centuries, humanity has looked to the stars with wonder, piecing together fragments of knowledge to understand the universe. But what if I told you that some of the biggest questions, the ones that could completely reshape science as we know it, remain unanswered? Today, we're embarking on a journey through 26 of the most baffling mysteries in space science, each one holding the potential to rewrite the rules of reality itself. Think about this for a moment. Everything we've ever discovered, from the laws of gravity to the birth of galaxies, started as a question. And right now, there are cosmic puzzles so profound that solving them could unlock technologies we've only dreamed of, or even reveal pathways to humanity's survival among the stars. Take dark matter, for example, an invisible force weaving through the cosmos, making up most of the universe's mass, yet completely undetectable to our instruments. Or consider the mind-bending possibility of parallel universes, where alternate versions of reality might exist just beyond our perception. These aren't just science fiction tropes, they're real, unsolved enigmas that keep scientists awake at night. What makes these mysteries so thrilling isn't just their complexity, it's what they represent. Every unanswered question is a door waiting to be opened, a chance to glimpse the universe in a way no one ever has before. And that's why this exploration matters, whether it's unraveling the true nature of black holes or figuring out if we're alone in the cosmos. Each discovery has the power to change how we see ourselves and our place in the grand scheme of things. So, if you've ever felt that pull of curiosity when you look up at the stars, you're in the right place. Get ready, because we're about to dive deep into the unknown, where the answers could be as extraordinary as the questions themselves. Imagine holding a map that shows only a fraction of the world's roads, cities, and landmarks all missing, leaving vast blank spaces where something clearly should be. That's exactly how scientists feel when they study the universe. We can see stars, galaxies, and cosmic dust, yet all of it accounts for less than 5% of everything that exists. The rest, a ghostly presence called dark matter, silently shaping the cosmos in ways we're only beginning to grasp. Here's what makes this so baffling. Dark matter doesn't absorb, reflect, or emit light. It's completely invisible, so how do we even know it's there? Picture a merry-go-round spinning at a playground. If you only saw the outer edge whirling wildly while the center stood still, you'd know something unseen was at work. That's what happens with galaxies. Stars on the outer rims move far faster than they should based on the visible matter alone, as if an invisible hand is holding them in place. Without dark matter's gravitational pull, galaxies would fly apart. The hunt to identify this elusive substance has led to some of the most creative experiments in science. Deep underground, in abandoned mines shielded from cosmic interference, detectors wait for the faintest whisper of a dark matter particle colliding with ordinary atoms. Meanwhile, particle smashers like the Large Hadron Collider recreate high-energy conditions of the early universe, hoping to produce and catch a glimpse of these shadowy particles. Some theories suggest dark matter could be made of WIMP, hefty particles that barely interact with normal matter. Others point to actions, hypothetical particles so lightweight they could slip through walls unnoticed. But what if dark matter isn't a particle at all? A daring few physicists argue that we might be misunderstanding gravity itself, that Einstein's equations, while brilliant, need revision on cosmic scales. It's a radical idea, but in science, the biggest breakthroughs often come from questioning the unshakable. solving this mystery wouldn't just fill in the gaps in our cosmic map. It could rewrite the rules of physics, revealing new layers of reality hiding in plain sight. And that's just the first piece of the puzzle. If the universe played fair, we wouldn't be here. That's the unsettling truth behind one of cosmology's greatest puzzles, the missing antimatter. According to every known law of physics, the Big Bang should have produced matter and antimatter in perfect, symmetrical amounts. These two opposites are cosmic twins, identical in mass but with opposite charges. When they meet, they annihilate each other in a flash of pure energy. So why does our universe contain galaxies, planets, and us, instead of just nothing? The numbers alone make this baffling. For every billion particles of antimatter created in the early universe, there were 1,000,000,001 particles of matter. That tiny imbalance, just one extra particle in a billion, is all that survived the annihilation. Everything we see around us, from the screen you're watching to the stars overhead, is built from that slender leftover fraction. The question haunting scientists is simple. What broke the symmetry? Enter CERN, the particle physics lab straddling the Swiss-French border. Deep underground, researchers trap antimatter in magnetic cages, studying it with laser precision. They've found something peculiar. Antimatter falls downward under gravity, just like normal matter. Its light spectra match too, but what if there's a subtle difference we haven't spotted yet? Some theorists believe certain particles might decay slightly differently between matter and antimatter, a phenomenon called charge parity violation. Finding even a minuscule discrepancy could explain why matter won the cosmic lottery. Then there's the wild-card possibility, entire regions of space made of antimatter hiding in the voids between galaxies. Astronomers scan for telltale gamma ray flashes, the signature of matter and antimatter colliding at cosmic borders. So far, silence. If antimatter galaxies exist, they're either vanishingly rare or impossibly distant. Unraveling this mystery wouldn't just rewrite cosmology textbooks. Antimatter packs staggering energy potential. A single gram could power a city for days. Right now, producing it costs far more energy than it releases, but understanding its scarcity might unlock ways to harness it. More profoundly, solving the antimatter riddle would answer why the universe favored our existence at all. It's a reminder that we're here against staggering odds, in a cosmos where even the laws of physics seem tilted in our favor. One moment, space is silent. The next, a blinding flash of radio waves erupts with the power of 500 million suns, then vanishes, leaving no trace. These are fast radio bursts, some of the most explosive and mysterious signals in the universe. Lasting barely a millisecond, they outshine entire galaxies before disappearing without explanation. For years, scientists dismissed them as glitches until they realized these bursts were real, cosmic, and utterly perplexing. So what could possibly generate such staggering energy in the blink of an eye? One leading suspect, magnetars, the corpses of dead stars with magnetic fields so intense they warp reality itself. Picture a neutron star, an object so dense a teaspoon of it would weigh 1 billion tons. Now crank its magnetic field up 1,000 trillion times. That's a magnetar. When their crusts crack under unimaginable strain, they might unleash bursts powerful enough to cross billions of light years. In 2020, astronomers caught one red-handed, linking a fast radio burst to a magnetar in our own galaxy. Case closed, not quite, because here's the twist. While magnetars explain some bursts, others refuse to fit. Certain signals repeat at random intervals, like a cosmic Morse code with no sender. Some even pulse with eerie regularity, like clockwork ticking across the void. Then there's the wow signal of fast radio bursts, a one-off event so perfectly timed and positioned that for a fleeting moment, even seasoned researchers held their breath. Could these be something more deliberate? Theories abound. Colliding neutron stars might create shockwaves bright enough to mimic bursts, or perhaps evaporating black holes predicted by Stephen Hawking release their dying energy in these brilliant flashes. Some even speculate about advanced civilizations harnessing unimaginable power, though most scientists consider that a last resort. The truth might be stranger still. What makes these bursts so tantalizing isn't just their mystery, but what they reveal. As they travel through space, they pick up traces of the universe's hidden matter, like cosmic fingerprints. Decoding them could map the invisible web of gas and dark matter threading the cosmos. And if we ever find a pattern that suggests intelligence behind them, well, that wouldn't just redefine astrophysics, it would redefine us. Until then, every burst is a reminder. The universe is louder, wilder, and far more mysterious than we ever imagined. What if everything you know, every star, every law of physics, every moment of history, is just one version of reality? The idea of a multiverse isn't just science fiction. It's a serious scientific hypothesis that could shatter our understanding of existence. Imagine a cosmic kaleidoscope where each turn creates a new universe with slightly different rules. In one, gravity might be stronger, making stars burn out faster. In another, atoms never formed, leaving behind a dark, empty void. And somewhere out there, there could be a universe where you made a different choice this morning, or never existed at all. This isn't just wild speculation. The math behind quantum mechanics and cosmic inflation, the theory explaining the universe's rapid expansion after the Big Bang, hints that multiple universes might be inevitable. When you zoom in on the quantum world, particles exist in a haze of possibilities until observed. Some interpretations suggest that every possible outcome does happen, just in a branching web of parallel realities. Meanwhile, cosmic inflation proposes that our universe is one bubble in a frothing sea of space-time, with other bubbles forever out of reach. But how do you prove something you can't see or touch? Scientists hunt for clues in the faint echoes of the Big Bang. If our universe collided with another long ago, the crash might have left scars in the cosmic microwave background, the afterglow of creation. Others look to quantum entanglement, where particles instantly influence each other across vast distances. Could this spooky connection be a thread linking parallel worlds? Skeptics argue these ideas border on philosophy, untestable by nature. Yet the stakes couldn't be higher. If true, the multiverse means our universe isn't fine-tuned for life. It's just one lucky roll of the dice in an infinite casino. The implications are dizzying. A multiverse could explain why fundamental constants, like the strength of gravity or the mass of an electron, seem perfectly set for life. In an infinite array of universes, some had to get it right, but it also raises unsettling questions. Are there versions of reality where black holes dominate or time runs backward? And if we're one universe among countless, does that make us insignificant or unimaginably rare? For now, the multiverse remains a tantalizing shadow on the edge of science. But if we ever find proof, it wouldn't just rewrite the textbooks. It would force us to rethink what it means to exist at all. At the heart of every black hole lies a riddle wrapped in darkness, a place where the laws of physics as we know them cease to make sense. Picture standing at the edge of a waterfall where the current grows so strong that not even light can fight its pull. That's the event horizon, the point of no return. But what happens to everything that crosses that threshold? For decades, scientists believed matter was crushed into an infinitely dense point called a singularity, where space and time simply end. Yet that answer raises more questions than it solves. How can something with infinite density exist in a universe built on finite rules? Enter wormholes, the cosmic shortcuts of science fiction that might just be real. Some theories suggest black holes don't destroy matter but funnel it through space-time tunnels, emerging who knows where. Imagine crumpling a piece of paper so two distant points touch, then poking a hole through them. That's the essence of a wormhole, and black holes could be the cosmic needles making it possible. But here's the catch: even if wormholes exist, they'd likely be unstable, snapping shut faster than anything could traverse them. Unless, of course, an unknown form of exotic matter could prop them open, a material with negative energy that defies gravity. We've never found such a thing, but its theoretical existence keeps this tantalizing idea alive. Then there's Stephen Hawking's bombshell discovery. Black holes aren't entirely black, they leak. Quantum mechanics dictates that pairs of particles constantly flicker in and out of existence at the edge of a black hole's grip. Sometimes one escapes while its twin falls in, slowly sapping the black hole's energy over eons. This Hawking radiation implies black holes have temperatures, lifetimes, and most perplexingly, a potential fate of evaporating into nothing. But if they vanish, what happens to all the information they swallowed? The laws of physics say information can't be destroyed, yet black holes seem to erase it. This paradox pits Einstein's relativity against quantum theory in a battle for the soul of physics. One audacious solution comes from the holographic principle, which suggests black holes don't destroy information, but encode it on their surfaces like a cosmic DVD. Every particle swallowed could be stored as a ripple on the event horizon, a two-dimensional imprint of three-dimensional reality. If true, it means the universe might operate like a hologram, with depth emerging from flat, intricate patterns. Proving this could bridge the gap between gravity and quantum mechanics, revealing a deeper layer of reality where space and time aren't fundamental but woven from something even stranger. The stakes couldn't be higher. Unlocking black holes' secrets wouldn't just satisfy cosmic curiosity, it could gift us technologies beyond imagination. Wormholes might offer paths to distant stars, while harnessed Hawking radiation could power civilizations. More profoundly, it would answer whether black holes are cosmic trash compactors or portals to something grander. For now, they remain the universe's ultimate vaults, guarding their mysteries behind walls of darkness. But every flicker of Hawking radiation, every theoretical breakthrough, brings us closer to cracking them open, and perhaps rewriting reality itself in the process. The universe isn't just expanding, it's doing so at a pace that defies logic, as if some unseen hand is pressing harder on the cosmic accelerator with each passing moment. This isn't a gentle drift of galaxies moving apart. It's a runaway expansion, and the culprit behind it is one of the most enigmatic forces in existence: dark energy. Think of it as the opposite of gravity, a repulsive force woven into the fabric of space itself, pushing everything apart faster and faster. But here's the catch: we have no idea what it actually is. When Einstein first introduced his theory of general relativity, he included a fudge factor called the cosmological constant, a mathematical placeholder to keep the universe static, as everyone assumed it was at the time. Later, when Edwin Hubble discovered the universe was expanding, Einstein called it his greatest blunder. But now, that very idea is back in play. Dark energy behaves eerily like Einstein's constant, a steady, invisible energy permeating empty space. Yet measurements show the expansion isn't just steady, it's speeding up. That suggests dark energy might not be constant at all, but something far stranger. Could it be a dynamic field, like an invisible ocean with currents that change over time? Some theories propose a quintessence field, a cosmic cousin to the Higgs field, but one that drives expansion instead of mass. Others wonder if dark energy is a sign of extra dimensions, hidden layers of reality where gravity leaks away, making it seem weaker in our observable universe. Then there's the most unsettling possibility, that dark energy's strength could grow exponentially, leading to a Big Rip scenario where not just galaxies, but atoms themselves are torn apart in a final, violent instant. The stakes are cosmic. Upcoming missions like the Euclid Space Telescope aim to map dark energy's fingerprints across billions of light years, measuring how it shaped the universe's large-scale structure. By studying the bending of light around galaxies and the distribution of galaxy clusters, scientists hope to tease out whether dark energy is truly constant or evolving. The answer could rewrite our fate. A steady dark energy means a slow, cold end, the heat death where stars burn out and space stretches into infinite silence. But if dark energy grows stronger, the universe might shred itself in a catastrophe that makes black holes look tame. What makes this mystery so thrilling is its sheer scale. Dark energy isn't just some distant curiosity. It makes up nearly 70% of the universe's total energy, yet it leaves no trace we can touch, no signal we can detect directly. It's the ultimate cosmic ghost, shaping everything while remaining utterly invisible. Solving it wouldn't just tell us how the universe ends. It could reveal whether our understanding of physics is missing a cornerstone, or whether we're standing on the edge of a revelation that redefines reality itself. The night sky holds billions of stars, each potentially hosting planets where life could thrive. We've discovered over 5,000 exoplanets, with many nestled in the Goldilocks zone, that perfect distance from their star where liquid water could pool. Statistically, the universe should be teeming with life, yet when we listen, the cosmos echoes with silence. This glaring contradiction is known as Fermi's paradox, and it cuts to the heart of one of humanity's oldest questions: are we truly alone? Consider the numbers for a moment. Our galaxy alone contains hundreds of billions of stars. Even if only a fraction of those have planets capable of supporting life, the sheer volume suggests civilizations should have arisen countless times over the universe's 13.8 billion-year history. So why haven't we found any traces? One unsettling possibility is that advanced civilizations tend to self-destruct, whether through war, environmental collapse, or technologies gone awry. It's a sobering thought, suggesting that the Great Filter, a hypothetical barrier preventing life from reaching interstellar scales, might lie ahead of us rather than behind. But maybe the answer isn't so dire. Perhaps intelligent life is simply rare or so different from our expectations that we fail to recognize it. Imagine an alien species that communicates through quantum entanglement or manipulates dark matter in ways we can't yet detect. Our current searches, like SETI radio telescopes or the James Webb Space Telescope's hunt for atmospheric biosignatures, might be looking for the cosmic equivalent of smoke signals in an age of fiber optics. Then there's the zoo hypothesis, the idea that advanced civilizations might be deliberately avoiding contact, observing us like wildlife in a cosmic preserve. It's a tantalizing thought, though impossible to prove. Others suggest we're simply too early to the party, that the universe's most prolific eras for life might lie billions of years in the future. The discovery of even microbial life beyond Earth would be revolutionary. A single cell on Mars or in the icy plumes of Europa's subsurface ocean would confirm that life isn't a fluke, it's a cosmic imperative. And if we ever intercept an artificial signal, that would rewrite not just science but philosophy, religion, and our very understanding of what it means to be human. Until then, the silence lingers, a vast and unanswered question hanging among the stars. Every story has a beginning, but what if the universe's origin story starts with a question we still can't answer? The Big Bang is often portrayed as a fiery explosion, but that's not quite right. It was the rapid expansion of space itself, a moment when all the energy, matter, and laws of physics we know unfurled from an unimaginably hot, dense state. Yet here's the puzzle. The Big Bang theory explains what happened after the beginning, not what caused it. What set this cosmic domino effect in motion? One possibility lies in the quantum realm, where particles flicker in and out of existence thanks to Heisenberg's uncertainty principle. Could the universe itself have emerged from a random quantum fluctuation, a tiny bubble of false vacuum that inflated exponentially? It's a mind-bending idea. Everything we see might owe its existence to a subatomic hiccup. String theory takes this even further, proposing that our universe is a three-dimensional brain floating in a higher dimensional space. A collision between two such brains could have unleashed the energy of creation, like cosmic sheets of paper slamming together to spark a fire. Then there's the cyclical model, where the Big Bang wasn't a true beginning but a rebound. Picture a universe collapsing inward under gravity until it reaches a point so dense it bounces back outward, a phoenix-like rebirth from its own ashes. This big bounce scenario suggests time might stretch infinitely in both directions, with no true start or end. But how do we test something that happened over 13 billion years ago? Clues might hide in the cosmic microwave background, the faint afterglow of the early universe. Patterns in this primordial light could reveal whether space-time carries scars from a pre-Big Bang era. Perhaps the most radical idea comes from holographic theory, which posits that our three-dimensional reality is a projection from a two-dimensional surface at the universe's edge. In this view, the Big Bang wasn't an explosion in space, but a rendering of information like a cosmic computer booting up. If true, it would mean time itself is an emergent property, not a fundamental feature of reality. The stakes here are cosmic. If time had a definitive beginning, it raises philosophical questions about what, if anything, came before. A cyclical or holographic universe, on the other hand, suggests existence operates on scales and principles we've barely begun to grasp. Solving this mystery wouldn't just rewrite cosmology, it would redefine our very understanding of existence. And that's the ultimate frontier, not just mapping the universe, but deciphering whether it's the first and only verse, or just one page in an infinite cosmic library. Black holes devour everything in their path, but what if the universe has cosmic fountains to match these cosmic drains? Enter white holes, the hypothetical opposites of black holes, where nothing can enter and matter erupts outward uncontrollably. While we've never observed one, their existence isn't just science fiction. Einstein's equations allow for them, painting a universe where every black hole might have a white hole counterpart, like two sides of the same cosmic coin. Imagine a black hole's event horizon in reverse. Instead of a point of no return, a white hole would have a point of no entry, a boundary where matter and light can only escape, never to return. Some theories suggest that when a black hole collapses, it might rebound as a white hole in a distant region of spacetime, spewing out everything it once consumed. If true, this could solve one of physics' biggest headaches, the black hole information paradox. Instead of data vanishing forever, it might be regurgitated elsewhere, preserving the universe's fundamental rules. But where would we even look for such an object? One tantalizing candidate is gamma-ray bursts, those unimaginably powerful explosions lighting up the cosmos. A handful of these events defy explanation, with energy signatures that don't quite match collapsing stars or colliding neutron stars. Could they be the death throes of white holes, blasting their contents into the void? Even wilder is the idea that the Big Bang itself was a white hole event, the ultimate cosmic eruption birthing our universe from the remnants of another. The implications are staggering. If white holes exist, they could act as bridges between universes, or even as time-reversed tunnels connecting distant epochs. Picture a black hole in our universe funneling matter into a white hole in another, creating a one-way passage to a reality with entirely different physical laws. Some models even suggest that miniature white holes could have formed in the early universe's chaos, lingering today as primordial anomalies, cosmic geysers hidden in plain sight. Of course, skepticism abounds. White holes violate the second law of thermodynamics by seemingly creating order from disorder. They are also notoriously unstable in theory, prone to collapsing the moment they form. Yet the very possibility challenges our understanding of causality and the nature of time. If we ever found definitive proof, a burst of particles with no conceivable source, or a region of space repelling all matter, it wouldn't just add a new object to the cosmic menagerie. It would force us to rethink how the universe balances creation and destruction, and whether the cosmos itself operates in cycles we're only beginning to glimpse. For now, white holes remain a beautiful enigma, a reminder that the universe's strangest ideas often lurk just beyond the edge of observation. Somewhere beyond the stars, an invisible hand is tugging at our galaxy along with thousands of others, toward a point in space we can't even see. Astronomers call this cosmic enigma the Great Attractor, and it's one of the most perplexing gravitational puzzles in the universe. Picture floating down a river, only to realize the current is pulling you toward a waterfall hidden by fog. That's the situation we're in. The Milky Way, along with our neighboring galaxies, is racing toward this mysterious region at over 2 million kilometers per hour. But here's the catch. When we point our telescopes in that direction, our view is blocked by a thick curtain of dust and stars from our own galaxy's disk. It's like trying to find a lighthouse while standing in a sandstorm. So what could possibly exert such a tremendous gravitational pull? Early theories suggested it might be a supercluster, a massive gathering of galaxies bound together by gravity. The Shapley supercluster, located even farther beyond the Great Attractor, was a prime suspect, but calculations showed its pull wasn't nearly strong enough to explain the motion we observe. Then came the realization that the Great Attractor might not be a single, dense object, but rather a sprawling concentration of dark matter, the invisible scaffolding that shapes the universe's large-scale structure. Imagine a mountain range made of shadow, its peaks and valleys sculpting the flow of galaxies like rivers around unseen terrain. Recent advancements, like the cosmic microwave background maps from the Planck satellite, have revealed even more complexity. The Great Attractor appears to be just one piece of a far vaster flow, part of what scientists call the Laniakea supercluster, a filamentary web of galaxies spanning 500 million light-years. Within this structure, our Milky Way is a mere speck, riding a gravitational current toward an unseen focal point. But the mystery deepens. Some researchers speculate that the Great Attractor could be a sign of something even more exotic, a cosmic defect in the fabric of space-time, a relic scar from the universe's earliest moments. The key to solving this riddle lies in new sky surveys, like those planned with the upcoming Square Kilometre Array radio telescope. By peering through the galactic dust with unprecedented clarity, we might finally glimpse what's pulling us in. Will it be a previously undiscovered cluster of galaxies, a knot of dark matter, or something entirely unexpected? The answer won't just satisfy scientific curiosity. It could redefine our place in the cosmos, revealing whether we're drifting toward a known structure or a gravitational anomaly that challenges our understanding of the universe itself. One thing's certain, the Great Attractor isn't just a destination. It's a cosmic compass pointing towards secrets we've only begun to imagine. Time bends like a river flowing forward, but what if it could twist back on itself? Einstein's theory of relativity suggests it's possible. Hidden within his equations are solutions called closed time-like curves, paths that loop back to their own starting point in spacetime. In theory, following one could let you travel to the past, meet your younger self, or even rewrite history. But here's the catch: the universe seems to hate paradoxes. Take the classic grandfather problem. If you went back and accidentally prevented your own birth, how could you exist to make the trip in the first place? It's a logical snake eating its own tail, and it's why many physicists dismiss time travel as fantasy. Yet the quantum world plays by different rules. In labs, particles entangled through quantum mechanics appear to influence each other instantaneously, as if information leaps across time. Some experiments even suggest particles can affect their own past states, like a cosmic game of telephone where the message arrives before it's sent. This isn't quite time travel, but it hints that at microscopic scales, causality might be more flexible than we thought. Imagine flipping a coin and seeing it land heads up, then, through some quantum quirk, retroactively ensuring it always landed that way. Reality, it seems, has loopholes. The real question is whether these quantum oddities could scale up. Enter cosmic strings, hypothetical defects in spacetime left over from the Big Bang, thinner than an atom but denser than a neutron star. If two of these strings raced past each other at near light speed, they might warp spacetime into a closed loop, creating a tunnel through time. Wormholes, too, could serve as shortcuts between eras, provided we find a way to stabilize them with exotic matter. The catch: both ideas require conditions so extreme they border on the impossible. A single cosmic string could stretch across the entire universe, and no one's sure they even exist. Then there's the ultimate mind bender. What if time travel is possible, but the universe self-corrects to prevent paradoxes? The Novikov self-consistency principle suggests any attempt to alter the past would inevitably reinforce what already happened. You might travel back to stop a disaster, only to realize your actions caused it in the first place. History becomes a locked puzzle, with every piece snapping into place no matter how you twist it. The implications are staggering. If time travel exists, even in theory, it would mean the future and past are as tangible as distant stars, places we could reach under the right conditions. It would blur the line between memory and prophecy, turning history into a landscape we could walk through. But until we find a cosmic string, unlock wormholes, or catch a particle breaking causality's rules, time travel remains the universe's ultimate what if. And that's the thrill of it, not just the science, but the tantalizing possibility that somewhere in the math, the cosmos left us a backdoor. All we have to do is find the key. Picture a planet with no sunrise, no sunset, just endless darkness as it drifts alone through the cold void between stars. These are rogue planets, cosmic nomads untethered from any solar system, and they might be the most common worlds in our galaxy. Unlike Earth, which basks in the warmth of the sun, rogue planets wander freely, their surfaces frozen and lightless. Yet despite their isolation, these dark worlds could hold secrets that rewrite our understanding of how planets form and where life might exist. How does a planet end up orphaned in the first place? Some are likely born that way, collapsing directly from dense gas clouds too small to ignite into stars, essentially failed stars that never grew large enough to shine. Others might be violently ejected from their home systems during gravitational tugs of war between young planets. Imagine a solar system in chaos, with giant planets like Jupiter slingshotting smaller neighbors into the abyss. Simulations suggest this could happen to Earth-sized worlds within the first million years of a system's life. leaving them to wander the galaxy eternally. But here's where it gets fascinating. A rogue planet doesn't have to be a frozen wasteland. Tidal forces from a massive core, radioactive decay, or even thick insulating atmospheres could trap enough heat to maintain subsurface oceans. Take Jupiter's moon Europa as an example, icy on the outside, but potentially harboring a liquid ocean beneath, warmed by gravitational squeezing. Now imagine a rogue planet with similar conditions, its hidden seas kept liquid by internal heat for billions of years. Could microbial life thrive in such a place? Astrobiologists think it's possible, turning these lone wanderers into stealth candidates for alien ecosystems. The hunt for these invisible worlds is like searching for black cats in a pitch-black room. Without a host star's light to illuminate them, rogue planets are nearly impossible to detect with traditional methods. That's where missions like NASA's upcoming Nancy Grace Roman Space Telescope come in. Using a technique called microlensing, it will watch for the subtle warping of starlight caused by a rogue planet's gravity, a fleeting distortion that betrays its presence. Early estimates suggest there could be trillions of them in the Milky Way alone, outnumbering stars by as much as 20 to 1. What if some of these rogue planets aren't just icy outcasts, but stolen worlds carrying life from one system to another? It's a wild thought. A planet ejected from a dying star system might drift for eons before being captured by another, seeding life across the galaxy like a cosmic pollinator. The more we learn about these shadowy nomads, the clearer it becomes the universe might be teeming with hidden worlds, silent and dark, each carrying stories we're just beginning to imagine. How big is the universe? The answer seems simple, just look as far as telescopes can see. But here's the catch: every measurement we've taken, from the cosmic microwave background to the large-scale distribution of galaxies, suggests space isn't just vast, it might be truly infinite. A flat universe, one without any measurable curvature, would stretch endlessly in all directions with no boundary, no edge, no outside. That's a staggering thought. It means no matter how far you traveled, you'd never hit a wall or loop back around. Just more galaxies, more stars, more emptiness forever. But how do we know for sure? The key lies in geometry. Imagine drawing a giant triangle across the cosmos with beams of light as its sides. In a positively curved universe like the surface of a balloon, those angles would add up to more than 180 degrees. In a negatively curved space, they'd sum to less. Yet every test, from NASA's W map to the Planck satellite, shows angles adding up to exactly 180 degrees. Flat, but here's the twist: a flat universe doesn't have to be infinite. It could also be finite but unbounded, like a video game world where exiting one edge brings you back to the opposite side. Topologists call this a torus shape, a cosmic donut where space folds in on itself in ways too vast for us to perceive. If the universe is infinite, the implications are mind-numbing. An endless expanse guarantees that every possible configuration of matter must repeat somewhere out there. There's an Earth identical to ours, down to the last atom. And not just one, an infinite number. Every choice you didn't make, every alternate version of history, every conceivable variation of reality would exist somewhere in the void. It's a concept so dizzying that even physicists struggle to wrap their heads around it. Yet doubts linger. Some theorists argue that subtle anomalies in the cosmic microwave background, unexplained cold spots or unusual alignments, could hint at a finite cosmos with complex topology. Others suggest that if the universe were infinite, the night sky should be blindingly bright, packed wall to wall with stars in every direction. This Olbers paradox was solved by the expansion of space, redshifting distant starlight into invisibility, but it's a reminder that infinity comes with paradoxes of its own. The truth might lie beyond our current tools. Future gravitational wave detectors or deeper cosmic microwave background maps could reveal telltale patterns repeating circles in the sky, like hall of mirror reflections betraying a folded universe. Or we might find that infinity isn't just a mathematical abstraction, but the inescapable reality we inhabit. Either answer would redefine our place in existence. Are we a single spark in a boundless cosmic bonfire, or just one tile in an impossibly vast but finite mosaic? For now, the question hangs in the void, as infinite as the possibilities it holds. On the morning of June 30th, 1908, a blinding fireball streaked across the skies of Siberia, followed by an explosion so powerful it registered on barometers 5,000 miles away. The Tunguska event wasn't just another meteor impact, it was a cosmic mystery that flattened 80 million trees across 800 square miles, yet left no crater behind. Eyewitnesses described a column of blue light moving across the sky, then a shockwave that knocked people off their feet and shattered windows hundreds of miles away. For decades, scientists have puzzled over what could unleash such devastation without leaving a trace. The leading theory points to a stony asteroid or comet fragment exploding in Earth's atmosphere, roughly 5 to 10 kilometers above the surface. At that altitude, the heat and pressure would have vaporized the object before it could hit the ground, releasing energy equivalent to 10 to 15 megatons of TNT, nearly 1,000 times more powerful than the Hiroshima bomb. But here's where things get strange. Typical airbursts from asteroids leave behind chemical traces like iridium or melted rock, yet Tunguska's soil samples show none of these. That absence has fueled wilder explanations, like a chunk of antimatter annihilating itself on contact with our atmosphere. While theoretically possible, there's no known natural process that could create and deliver such a concentrated antimatter mass across interstellar space. Then there's the black hole hypothesis, a microscopic singularity tunneling through Earth like a bullet through tissue paper. The math checks out. A black hole the mass of a small asteroid would be just the right size to pass through the planet without causing catastrophic damage, exiting somewhere in the North Atlantic. But it would leave telltale seismic ripples in its wake, and no such signal was recorded. Even stranger is the idea of a comet made of exotic mirror matter, a hypothetical substance that interacts with our world only through gravity. If such an object disintegrated above Siberia, it could explain the lack of debris, but it's a solution that raises more questions than it answers. What makes Tunguska so critical isn't just solving a century-old puzzle, it's preparing for the next one. Objects this size hit Earth roughly once every few hundred years, and the next could strike a populated area. Had the 1908 event occurred 4 hours later, it would have obliterated St. Petersburg. Modern detection systems like NASA Atlas and the upcoming Vera Rubin Observatory aim to spot incoming threats weeks or even years in advance, giving us time to deflect them. But Tunguska serves as a stark reminder. Some cosmic visitors still slip through unseen, and understanding their nature could mean the difference between a close call and a global catastrophe. Perhaps the most enduring lesson of Tunguska is how much we still don't know. Even with all our technology, the universe keeps surprising us, whether with airbursts that defy expectations or objects that vanish without a trace. Each unsolved event is a cosmic clue, waiting to reveal secrets about our solar system's history, the nature of space rocks, or even physics we've yet to discover. And until we find definitive answers, Tunguska remains a warning written across the Siberian wilderness, a reminder that the sky holds mysteries we're only beginning to comprehend. Imagine a celestial metronome so precise it rivals our best atomic clocks until suddenly, without warning, it stutters. Pulsars, the rapidly spinning corpses of massive stars, are nature's most reliable timekeepers, beaming radio waves with such regularity you could set your watch by them. But every now and then, they glitch a tiny, inexplicable speed-up that defies their usual rhythm. These cosmic hiccups might last milliseconds or stretch for minutes, and they're one of the strangest behaviors in the universe. What could possibly make a dead star stumble? The answer lies in the extreme physics of neutron stars, where matter is crushed to densities so insane a teaspoonful would weigh 1 billion tons. Picture a sphere just 12 miles across, yet packing more mass than our sun, spinning hundreds of times per second. Under that unimaginable pressure, protons and electrons fuse into neutrons, creating a superfluid, a bizarre state of matter with zero friction. Most of the star's interior flows like liquid helium on a cosmic scale, while the rigid crust, barely a kilometer thick, spins along with the magnetic field that generates the pulsar's beams. Here's where things get wild. When the superfluid's vortices, whirlpools of quantum chaos suddenly unpin from the crust, they transfer angular momentum outward, giving the star a speed boost like a figure skater pulling in their arms. Think of it as a cosmic backflow, the star's inner engine briefly outpacing its outer shell. Another possibility, starquakes. Neutron star crusts are under such immense strain that they occasionally crack, releasing pent-up energy like a planetary-scale tectonic shift. These fractures could alter the star's moment of inertia, causing it to spin faster to conserve angular momentum, a phenomenon eerily similar to how an ice skater spins quicker when they tighten their pose. But the real intrigue isn't just how these glitches happen, it's what they reveal. Each one is a tiny window into the behavior of matter under conditions we can't possibly recreate on Earth. By studying glitches, we're essentially performing cosmic autopsies on dead stars, decoding the physics of superfluid dynamics, nuclear postaphases, and even the hypothetical quark-gluon plasma that might lurk at their cores. Some pulsars, like the famous Vela pulsar, glitch every few years with startling predictability, while others remain silent for decades. That variation suggests neutron stars aren't monolithic. They might have complex inner structures as layered as an onion, with different regions rotating at varying speeds. There's even speculation that glitches could be triggered by external forces, perhaps a clump of infalling debris or a ripple in space-time itself. The stakes go beyond curiosity. Pulsars are used as galactic GPS beacons for deep space navigation, and their glitches could throw off future interstellar travel calculations. More profoundly, understanding these anomalies might help us unlock the equation of state for neutron stars, the holy grail of high-energy physics, revealing how matter behaves at the very edge of possibility. Every glitch is a cosmic telegram from beyond the grave, carrying secrets written in spin rates and quantum turbulence. And until we crack their code, these dead stars will keep us guessing, one erratic heartbeat at a time. We think we know what the universe is made of: atoms, stars, galaxies, the stuff we can see and touch. But here's the shocking truth. Everything we've ever observed, from the smallest grain of sand to the largest supercluster, makes up less than 5% of the cosmos. The rest, a cryptic cocktail of dark matter and dark energy, two invisible forces shaping the universe in ways we're only beginning to grasp. If the cosmos were a vast ocean, ordinary matter would be the scattered foam on its surface, while the depths below remain uncharted and alien. Let's start with dark matter, the universe's hidden scaffolding. Imagine watching a play where most actors are invisible. You can't see them, but you know they're there because the visible performers move in response. That's how we detected dark matter. Galaxies spin so fast that their stars should be flung into the void, yet something unseen holds them together. The gravitational pull suggests there's 6 times more dark matter than ordinary matter, woven through space like an invisible net. But what is it? The leading candidate is WIMP, weakly interacting massive particles, hypothetical entities that barely interact with light or matter. Underground labs hunt for them in ultra-sensitive detectors, waiting for the rare moment a WIMP bumps into an atomic nucleus. Others suggest actions, ghostly particles so light they could pass through a light year of lead without a trace. Then there's dark energy, the universe's mysterious accelerator. While dark matter pulls galaxies together, dark energy pushes them apart, an anti-gravity force driving the cosmos to expand faster and faster. Einstein's cosmological constant, once dismissed as his greatest blunder, might describe its steady presence. But measurements show dark energy's strength could be changing, hinting at something far stranger, perhaps a dynamic field called quintessence, or even a sign that gravity itself behaves differently on cosmic scales. Could dark matter and dark energy be two sides of the same coin? Some theorists propose they're manifestations of a single, unified dark fluid with properties that shift over time. Others suggest we're witnessing the fallout of a hidden dimension, where gravity leaks into our universe unevenly. The answers might lie in next-generation tools like the Vera Rubin Observatory, mapping billions of galaxies to trace dark matter's fingerprints, or the Euclid Space Telescope, probing dark energy's effect on cosmic expansion. What's at stake isn't just filling in a cosmic ledger, it's rewriting the rules of reality. If dark matter is a new particle, it could open doors to technologies we can't yet fathom. If dark energy evolves, it might decide whether the universe ends in ice or fire. And if these forces are linked, that could reveal a deeper layer of physics hidden in plain sight. For now, the universe's recipe remains a puzzle with 95% of the ingredients still missing. But every experiment, every observation, brings us closer to tasting the unknown. We take for granted that we live in a world of 3 dimensions: length, width, and height, with time as the fourth. But what if our reality is just the surface of something far deeper? String theory, one of the most ambitious frameworks in physics, suggests the universe might actually have 10 or 11 dimensions, with the extra ones curled up so tightly they're smaller than an atom. Think of it like a garden hose. From a distance, it looks one-dimensional, but up close, you see it has a circular dimension wrapped around its length. Now imagine that hidden geometry applied to the very fabric of space itself. These extra dimensions aren't just mathematical curiosities. They could solve some of physics' biggest puzzles. Why is gravity so weak compared to the other fundamental forces? One radical idea is that gravity isn't actually weak. It's just leaking into other dimensions, diluted across realities we can't perceive. Picture water seeping through a sponge. What we experience as gravity might be the leftover trickle from a much stronger force bleeding into unseen realms. Could some of these dimensions be larger than we thought? If even one extra dimension were as big as a millimeter, it would create detectable deviations in gravity's behavior at tiny scales. Experiments like the Large Hadron Collider search for particles that might briefly vanish into higher dimensions before reappearing, leaving behind telltale energy deficits. Other projects use exquisitely sensitive torsion balances to measure gravity's strength at microscopic distances, hunting for any hint that it strengthens unexpectedly, a sign we're brushing against hidden geometry. Then there's the wildest possibility of all, that entire universes exist parallel to ours, separated by a dimensional veil. These brain worlds could float just millimeters away in a higher dimension, completely invisible yet potentially governed by different physical laws. Collisions between such brains might even explain cosmic anomalies like the Big Bang itself. The implications are staggering. If extra dimensions exist, they could unlock technologies straight out of science fiction, wormholes for interstellar travel, shortcuts through space-time, or even communication between realities. More profoundly, they'd rewrite our understanding of existence, revealing that everything we know is just a slice of a far richer, stranger cosmos. Until we find definitive proof, these dimensions remain tantalizing shadows at the edge of science, but every experiment brings us closer to peeling back the layers of reality itself. Neutron stars are nature's most extreme laboratories, cosmic pressure cookers where matter is squeezed to the brink of impossibility. Picture crushing the entire mass of our sun into a sphere no wider than Manhattan, and you'll start to grasp the mind-bending physics at play. The gravitational forces are so intense that atoms collapse, electrons merge with protons, and what remains is a sea of neutrons packed tighter than anything else in the known universe. But here's the real mystery. Even after decades of study, we still don't know what happens at the very heart of these stellar corpses. Take a single teaspoon of neutron star material. On Earth, it would weigh 1 billion tons, so dense that if you dropped it, it would slice through the planet like a bullet through tissue paper. Yet the surface is just the beginning. As you dive deeper, the pressure mounts to levels that defy imagination, warping matter into forms we've never seen. Some theories suggest the core might dissolve into quark-gluon plasma, a primordial soup of particles that last existed microseconds after the Big Bang. Others propose even stranger possibilities, like nuclear pasta, layers of neutron-rich material twisted into shapes resembling spaghetti or lasagna by the crushing gravity. The breakthrough in cracking these secrets came from an unexpected source: ripples in spacetime itself. When two neutron stars spiral into each other and collide, they send gravitational waves echoing across the cosmos, carrying encoded details about their internal structure. In 2017, the LIGO and Virgo observatories detected such a collision, and the data revealed tantalizing clues. By analyzing how the stars deformed before merging, scientists got their first indirect glimpse into the physics of neutron star interiors. The findings hinted that these objects might be softer or more malleable than previously thought, a surprise that's forcing us to rethink what happens under such extreme conditions. But the enigma only deepens. Some models suggest neutron stars could harbor cores of hyperion's exotic particles heavier than neutrons that form under insane pressures. Others speculate about strange stars, where neutrons break down into a sea of free-floating strange quarks, creating a superfluid with properties beyond anything in our current physics textbooks. Then there's the wild card, pion condensates, a theoretical state where particles called pions form a crystalline lattice inside the star, turning it into a cosmic superconductor. What makes this puzzle so urgent isn't just curiosity. It's a chance to probe the fundamental laws of nature. Neutron stars are the only places in the universe where we can study matter at densities impossible to replicate on Earth, offering insights into everything from quantum chromodynamics to the origins of heavy elements like gold and platinum. Future gravitational wave detections, paired with next-generation telescopes like the Square Kilometre Array, could finally decode these cosmic enigmas. And when they do, the answers might rewrite our understanding of reality itself, one crushed neutron at a time. The moon shouldn't exist, at least not the way we know it. Here's why: when Apollo astronauts brought back lunar rocks in the 1960s and 70s, scientists made a startling discovery. The moon's chemical fingerprint, its mix of oxygen, titanium, and other isotopes, was nearly identical to Earth. Not just similar, but a near-perfect match. That's bizarre because every other body in the solar system, from Mars to meteorites, carries distinct isotopic signatures. So why does our moon, a world 238,000 miles away, look like it was carved from the same cosmic clay as Earth. One leading theory is the giant impact hypothesis, a cataclysmic collision between a young Earth and a Mars-sized object called Theia. In this violent scenario, debris from the smash-up would have coalesced into the Moon, explaining the shared chemistry. But there's a problem. Computer simulations show that most of the Moon should have come from Theia, meaning its composition ought to differ from Earth. Unless, of course, Theia was isotopically identical to Earth, a statistical long shot, or the collision was so extreme it vaporized both bodies, thoroughly mixing their material before the Moon formed. New wrinkles keep emerging. Some lunar rocks contain volatile elements like zinc, which should have boiled away in a high-energy impact. Others show traces of water locked in minerals, hinting the Moon wasn't entirely scorched dry. Could Theia have struck at a glancing angle, leaving Earth's mantle relatively undisturbed while still ejecting enough material to form the Moon? Or was the impact slower and wetter than we thought, preserving more of Earth's original chemistry? Upcoming missions aim to crack this mystery. NASA Artemis program plans to land astronauts near the lunar South Pole, where ancient crust untouched by lava flows might hold primordial clues. China's Chang missions are collecting samples from the far side, a region geologically distinct from the familiar near side. Even tiny differences in isotope ratios could rewrite the Moon's origin story, revealing whether it was born from a single apocalyptic crash, a series of smaller impacts, or something even stranger. The stakes go beyond lunar history. If giant impacts are common in young planetary systems, then Earth-like worlds with large moons might be rare or essential for stabilizing climates and enabling life. Our Moon's gravity slows Earth's rotation, taming extreme weather and creating tides that could have nurtured early biology. Solve its origin, and we might finally understand whether life-friendly worlds are cosmic flukes or inevitable outcomes. For now, the Moon keeps its secrets close, a silent witness to the chaos that shaped our corner of the universe. Every second, trillions of invisible bullets tear through Earth cosmic rays, atomic fragments hurtling through space at nearly the speed of light. Some pack so much energy they make the Large Hadron Collider look like a toy, striking our atmosphere with the force of a fastball. Yet despite bombarding us for over a century since their discovery, these subatomic travelers guard their origins fiercely, turning one of space's most pervasive phenomena into one of its greatest puzzles. Where does such staggering energy come from? One prime suspect: supermassive black holes at the hearts of active galaxies. As these monsters devour matter, they spew jets of plasma stretching millions of light-years, cosmic particle accelerators far more powerful than anything we could build. When these jets slam into interstellar gas, they might forge ultra-high-energy cosmic rays like sparks from a celestial anvil. Another contender, gamma-ray bursts, the universe's most violent explosions. The afterglow of these stellar catastrophes could act as a natural synchrotron, boosting particles to energies 100 million times beyond what our best labs achieve. But here's where it gets weird. The highest energy cosmic rays ever detected, dubbed "Oh my God" particles, carry as much kinetic energy as a baseball pitch in a single proton. Nothing in known astrophysics should be able to accelerate particles to such extremes without breaking Einstein's speed limit. Some theorists suggest these outliers might be the death cries of hypothetical super-heavy dark matter particles, annihilating in bursts of exotic physics. Others propose their signatures of cosmic defects, cracks in space-time left over from the Big Bang, snapping like rubber bands to release pent-up energy. The hunt for answers isn't just academic. Cosmic rays constantly pepper astronauts and satellites, posing a radiation hazard for future Mars missions. They've even been blamed for causing glitches in airline electronics and triggering lightning storms. Understanding their sources could help us shield technology or even harness their energy. Projects like the Pierre Auger Observatory in Argentina use vast arrays of detectors to trace cosmic rays back to their origins by studying the particle showers they create in the atmosphere. Meanwhile, space telescopes like Fermi scan for gamma-ray clues that might link these rays to distant cosmic engines. What makes this mystery so compelling is its sheer scale. The highest energy cosmic rays are rare, striking each square kilometer of Earth only once per century. Yet their existence challenges our understanding of physics, hinting at cosmic processes far more violent than we've imagined. Every time one of these particles slams into our atmosphere, it carries a message written in tera-electron volts, a telegram from the universe's most extreme environments. Decoding it could reveal black holes' inner workings, expose dark matter's fingerprints, or uncover entirely new physics lurking in the voids between galaxies. Until then, the sky remains a shooting gallery of atomic mysteries, each impact a reminder of how much we have yet to learn. Magnetic fields are the silent architects of the cosmos, invisible threads weaving through galaxies, guiding the birth of stars and sculpting the very structure of the universe. Yet despite their influence, we're only beginning to understand where these fields come from or how they shape galactic evolution. Picture a galaxy like our Milky Way, a swirling disk of gas, dust, and stars, all threaded by magnetic forces so pervasive they stretch hundreds of thousands of light years into intergalactic space. These fields aren't just passive observers, they're active players, accelerating cosmic rays, compressing gas clouds into stellar nurseries, and even channeling the flow of matter into supermassive black holes. So how does a galaxy become magnetized in the first place? One theory suggests the seeds were planted in the universe's infancy, when quantum fluctuations during the Big Bang imprinted weak magnetic fields across the primordial plasma. Over billions of years, as gravity pulled matter into galaxies, these fields could have been amplified by the churning motion of gas and stars like a cosmic dynamo, twisting and stretching magnetic lines until they grew strong enough to shape entire galaxies. But there's a catch. Primordial magnetism should have left faint traces in the cosmic microwave background, and so far, we've found no such signal. That's led scientists to consider another possibility. Magnetic fields might be self-made, forged in the furnaces of stars and supernova. When massive stars explode, they spew out magnetized plasma, seeding their surroundings with magnetic energy. Over time, galactic winds and turbulence could spread this magnetism like ink in water until it permeates the entire galaxy. The problem: simulations show this process might take too long to explain the strong fields we see in young, distant galaxies. Enter a new generation of radio telescopes, like the Square Kilometer Array and the Atacama Large Millimeter Array, designed to map galactic magnetism with unprecedented precision. By studying the polarization of radio waves, how their electric fields align as they pass through magnetized space, we can trace magnetic fields in regions too cold or dark for optical telescopes to see. Already, these instruments have revealed bizarre structures, magnetic filaments looping around black holes, spiral patterns aligning with galactic arms, and even vast cosmic webs of magnetism stretching between galaxies. The implications go far beyond curiosity. Magnetic fields may determine whether a galaxy becomes a vibrant star factory or a quiet backwater. In the turbulent hearts of molecular clouds, these fields can slow gravitational collapse, regulating how many stars form and how massive they grow. Too strong and star formation chokes off, too weak, and galaxies burn through their gas too quickly. Some theorists even suggest magnetism could solve the mystery of ultra-diffuse galaxies, faint, ghostly islands where stars are scarce, possibly because their magnetic fields siphoned away the gas needed to shine. What makes this mystery so electrifying is its sheer scale. If magnetism is indeed primordial, it could be a relic from the universe's first moments, carrying secrets about inflation or hidden dimensions. If it's stellar in origin, it might reveal how galaxies bootstrap themselves into complexity. Either way, the answers will rewrite our understanding of cosmic evolution, proving that even the most invisible forces can leave the boldest marks on the universe. Will the universe end in fire, ice, or something stranger? The answer lies in a cosmic tug of war between dark energy's relentless push and dark matter's gravitational pull. Right now, dark energy is winning, accelerating the expansion of space so fast that distant galaxies will eventually vanish beyond an invisible horizon, leaving our cosmic neighborhood cold and isolated. This is the heat-death scenario where stars burn out, black holes evaporate, and the universe fades into an endless, silent darkness. But it's not the only possibility. What if dark energy weakens over time? If gravity regains the upper hand, the expansion could slow, halt, and reverse, triggering a big crunch. Galaxies would rush toward each other, space would contract, and everything would collapse back into a singularity, mirroring the Big Bang in reverse. Some theories suggest this collapse might not be the end, but a rebirth, a big bounce where the universe recycles itself in an infinite cycle of expansion and contraction. Each iteration could tweak the laws of physics slightly, creating a new cosmos with different constants. Then there's the wild card, vacuum decay. Our universe might be resting in a false vacuum, a seemingly stable state that's actually a precarious ledge. If a quantum fluctuation tips space into a lower energy state, it could unleash a bubble of true vacuum expanding at light speed, rewriting the fundamental laws of physics as it goes. One moment, reality operates as usual, the next, atoms, forces, even time itself could cease to function in ways we recognize. The key to unraveling this cosmic endgame lies in mapping the universe's expansion with even greater precision. Projects like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope will measure supernova and galaxy clusters across billions of light years, tracking whether dark energy's strength is truly constant or subtly changing. Even tiny deviations could signal whether we're headed for eternal stillness, catastrophic collapse, or something beyond our current imagination. Perhaps the most profound realization is this: the fate of the universe isn't some distant abstraction. It's written into the fabric of reality here and now. Every galaxy we observe, every particle we detect, carries clues about how the story ends. And while the scales may tip toward cold oblivion for now, the universe has a habit of surprising us. After all, it's already done the impossible once. It created us. Whatever comes next, the final chapters promise revelations that could redefine existence itself. Most stars shine with reassuring predictability, their light as steady as a heartbeat. But scattered across the cosmos are celestial rebels, stars that flicker, fade, and flare without warning, defying every textbook explanation. Take Tabby's star, officially known as KIC 8462852. This otherwise ordinary star, 1,200 light-years away in Cygnus, made headlines when astronomers noticed its light dimming by up to 22% in erratic, unpredictable dips, far too extreme for any known planetary transit or stellar activity. Some researchers initially floated an electrifying possibility. Could this be evidence of an alien megastructure, like a Dyson swarm of energy collecting satellites? While that idea captured imaginations, the truth is likely stranger than fiction. Further observations revealed the dimming wasn't perfectly symmetrical, a telltale sign that something natural, if bizarre, was at work. One leading theory suggests vast swarms of comets or fragments from a shattered planet might be orbiting the star in chaotic clouds, blotting out its light in irregular patterns. Others point to colossal dust storms stirred by gravitational tugs from unseen companions. But here's the twist: Tabby's star isn't alone. Across the galaxy, variable stars like Betelgeuse, a red supergiant that recently dimmed dramatically before brightening again, hint at processes we're only beginning to grasp. Some pulsate rhythmically due to internal pressure changes, while others erupt unpredictably when magnetic fields snap and reconnect, unleashing storms of stellar fury. The hunt for answers has turned into a cosmic crowdsourcing effort. Projects like Planet Hunters enlist amateur astronomers to sift through data from telescopes like Kepler and TESS, spotting anomalies that algorithms might miss. These citizen scientists have already uncovered dozens of similarly odd stars, each with its own peculiar light curve. One star in the constellation Scorpius, for example, dims and brightens in a pattern that looks almost intentional. While natural explanations like dusty debris disks or binary star interactions remain most likely, the sheer diversity of these anomalies suggests our models of stellar behavior are missing critical pieces. What makes these stellar mysteries so compelling isn't just the what, but the why. Variable stars aren't mere curiosities, they're cosmic laboratories. By studying them, we're probing the extremes of stellar evolution, testing how stars interact with their environments, and even refining our search for extraterrestrial technosignatures. Every erratic flicker is a clue, a challenge thrown down by the universe, and as telescopes grow more sensitive and AI tools more sophisticated, we're closer than ever to decoding their secrets, whether they're whispered by dust clouds, screamed by magnetic upheavals, or just maybe engineered by intelligence beyond our own. Black holes don't just swallow matter, they devour information, and that's a problem. When Stephen Hawking first proposed that black holes could slowly evaporate through quantum effects, he stumbled into a paradox that's haunted physics for decades. If a black hole vanishes, what happens to all the data about the particles it consumed? Quantum mechanics insists information can never be truly destroyed, yet black holes seem to erase it permanently. This contradiction isn't just academic, it's a battle for the soul of reality, forcing us to choose between Einstein's gravity and quantum theory. One radical solution comes from the holographic principle, the idea that all the information swallowed by a black hole isn't lost but encoded on its event horizon like a cosmic fingerprint. Think of it as a three-dimensional movie projected from a two-dimensional screen. Every particle falling in could leave an imprint on the surface, preserved in swirling patterns of quantum bits. When the black hole evaporates, that data isn't erased, it's radiated back out, scrambled but intact in the Hawking radiation. It's a beautiful idea, but there's a catch. If information escapes, it implies the event horizon isn't the smooth gateway Einstein predicted. Instead, it might be a seething firewall of high-energy particles, incinerating anything that crosses. The firewall hypothesis is as shocking as it sounds. Imagine diving into what you think is a calm pool, only to hit a wall of flames the moment you breach the surface. This violent scenario emerges from calculations showing that for information to escape, the entanglement between particles inside and outside the black hole must break, a process so energetic it would ignite the horizon. But firewalls contradict relativity, which says free-falling observers should experience nothing unusual at the event horizon. So who's right? Enter complementary, a compromise suggesting both perspectives are valid, just from different viewpoints. To an outside observer, information piles up at the horizon, creating a firewall. To someone falling in, space-time remains smooth. It's as if reality itself has multiple layers, each telling a different but equally true story. The stakes couldn't be higher. If information escapes, it hints at a universe where space-time and gravity emerge from something deeper, perhaps a quantum code written on the boundaries of reality. If it doesn't, we might need to rewrite quantum mechanics. Experiments to test these ideas are as audacious as the theories themselves. Gravitational wave detectors could someday spot echoes of firewalls in black hole collisions, while quantum computers might simulate holographic encoding. Ultimately, this isn't just about black holes. It's about whether the universe is fundamentally predictable, orderly, and knowable, or if at its core, reality keeps secrets even physics can't unlock. The answer won't just settle a decades-old debate. It could reveal whether we live in a cosmos that remembers or one that forgets. We can see galaxies nearly 13 billion light-years away, their light stretching back to the dawn of time, but that's just the tip of the cosmic iceberg. The observable universe, a sphere 93 billion light-years across, is all we'll ever know. Beyond that, space expands faster than light can travel, locking away whatever lies past the horizon forever. It's like being stranded on an island, surrounded by an ocean we can never sail. But here's the haunting question. If we're limited to our tiny pocket of reality, how do we even begin to guess what's out there? One possibility is an infinite multiverse of bubble universes, each with its own laws of physics. Picture a pot of boiling water, with new bubbles constantly forming and drifting apart. According to inflationary theory, our universe might be one such bubble, born from a speck of false vacuum that expanded exponentially in the first fraction of a second after the Big Bang. If inflation never stopped, just slowed in our region, then beyond our cosmic horizon, space could still be spawning endless new universes, some with stars and life, others dark and empty. It's a dizzying thought, a fractal sea of realities where the constants of nature shift like sand, and our universe is just one grain on an infinite shore. But infinity isn't the only option. The cosmos might curve back on itself like the surface of a four-dimensional balloon. In this closed universe scenario, traveling far enough in one direction would eventually bring you back to where you started, though expansion would make the trip impossible. Alternatively, space could be flat and finite, like a video game world with invisible edges. The cosmic microwave background holds subtle clues, patterns in its light that might reveal whether space loops or stretches forever. So far, the data suggests flatness, but the margin of error leaves room for surprises. Then there's the wild card, other dimensions. String theory proposes that our universe is a three-dimensional brain floating in a higher dimensional space, like a sheet of paper in a vast library. Other brains could hover millimeters away in an unseen dimension, their gravity faintly tugging on ours. If true, the beyond might not be distant, just hidden, separated by a fold in reality we can't perceive. The irony is crushing. We're surrounded by the answers, yet forever barred from them by the speed of light and the accelerating expansion of space. Future civilizations, no matter how advanced, will inherit the same cosmic blindfold. But perhaps there's a loophole. If dark energy weakens, distant galaxies now racing away might one day slow, then reverse, bringing their light and their secrets back into view. Or maybe the key lies in gravitational waves, ripples from events so ancient they predate the observable universe itself. Until then, the great beyond remains the ultimate frontier, not just of space, but of imagination. Whether it's an infinite kaleidoscope of universes or a solitary cosmos adrift in nothingness, the mystery forces us to confront the limits of knowledge itself. And that's the paradox. The more we learn, the clearer it becomes how much we'll never see. Yet somehow, that's what makes the question so exhilarating. Because in the end, the universe isn't just expanding, so are the possibilities. What if consciousness isn't just something that happens inside our brains? What if it's woven into the fabric of the universe itself? This might sound like science fiction, but some scientists and philosophers argue that the line between mind and matter might be far blurrier than we've ever imagined. Take quantum mechanics, for example. At the subatomic level, particles exist in a haze of possibilities until they're observed almost as if reality itself requires a witness to take shape. Could this strange behavior hint at a deeper connection between consciousness and the cosmos? One radical idea comes from the theory of orchestrated objective reduction, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that tiny structures inside our brain cells called microtubules might harness quantum vibrations to produce consciousness. These vibrations, flickering at the very edge of quantum physics, could collapse into definite states, creating moments of awareness like frames in a film. Even wilder is the implication. If consciousness relies on quantum processes, it might not be confined to brains at all. The universe itself could possess a primitive form of awareness, with stars, galaxies, or even space-time subtly feeling their own existence. This idea aligns with panpsychism, an ancient philosophy gaining traction in modern science. Panpsychists argue that consciousness isn't an emergent property of complex systems like brains, but a fundamental feature of reality, like mass or charge. In this view, even electrons or atoms might have a sliver of subjective experience, not thoughts or emotions, but a raw, elemental awareness. Think of it like this: just as gravity exists everywhere, from planets to pebbles, consciousness could be a spectrum, scaling up from particles to humans in richness and complexity. Skeptics, of course, point out the lack of direct evidence. How would you test whether a rock has an inner experience? Yet intriguing clues linger. Studies show that anesthetics, which switch off consciousness, seem to disrupt quantum coherence in microtubules, while psychedelics, known to intensify awareness, enhance their vibrational states. Even the brain's electromagnetic fields, once thought too weak to influence neurons, might create a quantum environment delicate enough to support conscious perception. The implications are staggering. If consciousness is cosmic, it could solve the hard problem of why subjective experience exists at all. It might also reshape our search for extraterrestrial intelligence, not as radio signals or megastructures, but as patterns of self-organizing energy humming through the void. Some theorists even speculate that black holes, those ultimate cosmic paradoxes, could be knots of space-time where universal consciousness folds back on itself. Of course, this remains speculative, straddling the line between physics and metaphysics, but that's what makes it thrilling. Whether consciousness is a fluke of biology or a fundamental force, the question forces us to confront the deepest mystery of all. Why does the universe seem to know itself through us? And if we're the universe's way of experiencing itself, what else might be out there watching, wondering, and waiting to be seen? These 26 cosmic mysteries aren't just gaps in our knowledge, they're doorways to revolutions we can't yet fathom. Every unanswered question, from the true nature of dark matter to the possibility of parallel worlds, isn't a dead end but an invitation. Think of the scientists who once laughed at the idea of black holes, only for them to become the cornerstone of modern astrophysics. The universe has a habit of turning yesterday's impossibilities into today's textbooks. What makes these puzzles so electrifying isn't just their complexity, it's what they represent for us. Every time we peer deeper into the cosmos, we're not just discovering distant stars or exotic particles, we're uncovering pieces of a story that includes all of us. Take the hunt for extraterrestrial life. Whether we find microbes on Mars or decode an alien signal, the answer won't just fill a scientific niche. It'll redefine what it means to be human in a vast, interconnected cosmos. And the best part, you don't need a telescope or a particle accelerator to be part of this adventure. The moment you look up at the night sky and wonder why, you're stepping into the same current that's carried explorers, philosophers, and scientists for millennia. Maybe you're captivated by the eerie silence of Fermi's paradox, or the way quantum mechanics twists reality into knots. Whatever sparks your curiosity, that's where the next breakthrough might begin, because history shows the biggest leaps often come from asking the simplest questions. So let's keep pulling those threads. Share which mystery grips you in the comments. Is it the great Attractor's invisible tug, the secrets locked inside neutron stars, or something else entirely? This isn't just a conversation about the universe, it's a conversation with it. Hit subscribe to join us as we chase these enigmas across the cosmos, because the next chapter of discovery isn't just waiting to be written. It's waiting to surprise.